Hello everyone, my name is Miead Tehrani Moayyed. I'm fifth year PhD student at Northeastern University. On behalf of Institute for the Wireless Internet of Things at Northeastern University, let me welcome you to this session that we want to talk about creating RF scenarios for large-scale real-time wireless channel emulators. As an introduction, we talk about wireless experimental platforms and wireless network emulators. Then we talk about how we can model realistic RF channel emulation in emulators that consist of RF emulation scenario, channel characterization, multipath clustering, and tap approximation, and finally, channel impulse response resampling. Then we show an example in line of sight scenario. After that, we show you the goodness of this approximation process and wrap up in a conclusion slide. Wireless experimental platforms allow researchers to test their solution in realistic setups. They virtualize protocol stack on general purpose white box hardware connected to programmable radios. They promote reproducible results by enabling users to package their solution in shareable virtualized containers. Available testbeds are Powder, Cosmos, and AirPod. These platforms have some constraint. For example, they are specific to the hardware and they have topology and physical location of the devices as constraint. On the other hand, wireless network emulators can bring the RF scenario into the lab by bringing them into a processing box that act as a channel emulators. Basically, the channel impulse response of the scenario can be convolved with the transmit signals of all the transmitter and combined together to act as a received signal. So these wireless network emulators are not site-specific and there is no constraint to a specific hardware topology. So user can test solution in large variety of wireless configuration, for example, urban and rural scenario. And also the number of nodes can be variable and different traffic pattern and mobility can be implemented. However, emulation quality depends on how realistically the emulator can mimic the real-world environment. Design of large wireless network emulators require a trade-off between the accuracy and resources because the convolution in that FIR filters in a channel emulator has some computational complexity. So emulators support a limited number of non-zero FIR filter tabs. Therefore, creating RF scenario is an interesting and non-trivial problem. As an example, Colosseum is the largest world wireless network emulator. It consists of 256 software-defined radios that are fully programmable, and real-world scenario can be implemented via fabric of FIR filter implemented in FPGA that can implement or emulate around 65,000 channel in real time. Colosseum is capable of emulating wireless channel effects such as path loss, multipath and fading. Large-scale experimentation of wireless RF system with hardware in the loop is the thing that Colosseum is capable of. So as you can see, Colosseum can emulate wireless scenarios at the RF level. However, the emulation of the channel will be in the digital baseband IQ samples. As a contribution of this proposed method, we propose a new framework to create RF scenario for time domain FIR filter-based channel emulators that optimally scale down the ray tracer output to determine the non-zero taps of emulator FIR filter. We consider wireless scenario with rich RF information produced by a professional-grade ray tracing software. Then we study the proposed method in both line of sight and non-line of sight scenarios, and then we replicate the same scenario in the Colosseum wireless network emulator. Finally, we benchmark the approximated channel of the proposed method against the K strongest path approximation, which is a baseline method, and the original ray tracer channel. Now let's talk about modeling realistic RF channel emulation, which the overflow is as the following. First, channel characterization, then multipath clustering, and tap approximation, and ultimately channel impulse response resampling. And then we show you an example in a line of sight scenario. As a scenario, we consider Northeastern University scenario, an outdoor portion of the Boston campus. We use REMCOM wireless insight ray tracer as a tool for ray tracing, channel simulation, and for accurate ray tracing result. We use a high resolution 3D model that the total faces in this model is around 13,000. And then for more accurate result, we applied material properties for carrier frequency from the ITU recommendation. For a wireless scenario parameters, we focus on the LTE device-to-device communication in the carrier frequency of 2.3 gigahertz and the signal bandwidth of 20 megahertz. The UE transmitter power is 24 dBm, and the antenna gain pattern and all these parameters are listed in this table. On the right-hand side, you will see the hypothetical position of the receiver in the line of sight scenario and non-line of sight scenario. Now, once we implement this network and run the simulation in the ray tracer software, we will get the paths between the transmitter and receiver, and all these paths are color-coded by the received power from the transmitter to receiver on the left-hand side. On the right-hand side, once we have the transmit power and receive power signal, we can extract the channel impulse response, which is represented on the right-hand side as a path gain in logarithmic scale. Now we want to group all these paths that is a random number depending on the environment into just K group, which is the non-zero number of taps. For the Colosseum, it's 4 non-zero taps. So we use K-means machine learning algorithm for clustering multipath components. This algorithm finds clustered centroids by iteratively optimizing the position of the centroids. Then it grouped the data points, minimizing the sum of distances between the cluster data points to the respective cluster centroid. We can use this algorithm for the multi-dimensional data, such as the data that we have in this work, that is all the parameter of the paths. So basically, in this equation, it shows how it can minimize the sum of distances. So this is a distance-based clustering algorithm. So we need to have a reasonable and suitable distance function for clustering multipaths. So we use path parameters as the features, and these parameters are time of arrival, azimuth and elevation in the angle of arrival, and azimuth and elevation in angle of departure. So there are some challenges with this type of data. First is time of arrival and angular characteristic are not in the same scale. For example, time of arrival may be in the nanosecond. However, angular characteristic may be in the minus pi to pi. And also the second challenge is that the angles have periodic characteristic that make some challenges finding the distance and averaging the elements to find the new center in the K-means clustering algorithm. The ultimate solution for that is multipath component distance, MCD, which is first introduced by Gustafsson at 2014. This distance function maps the multipath component into a unit sphere and can scale time of arrival and the angles in the same scale. These are the equation that is used for this component distance. After using this distance function and run K-means with the non-line of sight scenario that I just showed you before with the received power, we can cluster those paths into four groups. These groups are shown in the left-hand side. You will see how these paths are grouped with the same color. On the right-hand side, you can find the channel impulse response, which is grouped into four groups. And each group has the same color. Now we want to approximate this group to one representative tab that we can have in the Colosseum example, 4 tabs. So to reconstruct the approximated tab, we need tab gain and tab's time of arrival. Tab gains can be calculated as a coherent summation of the path gain of each cluster, which consists of magnitude and phase of each path in each cluster. And the time of arrival of that tab is the cluster center's time of arrival. So on the right-hand side, you will see the thick stem are the approximated tabs that we have 4 approximated tabs with different color. Now, we need to resample this approximated channel impulse response tab into the tab that the network emulator can be digest. So basically, resample approximated channel impulse response derive the match index of the channel emulator FIR filters for each tab. Tabs are complex value IQ component that can be used as the input to FIR filter channel emulators. As an example, on the right-hand side, you will see 4 non-zero tabs prepared for the Colosseum channel emulator with 512 FIR filter tabs and 10 nanosecond sampling interval. You will see that the closest index get the tabs gain. Now, I would like to show you this process in the line of sight scenario that we have a dominant tab, line of sight tabs that we need to increase the weight of the time of arrival against the angles in order to represent the same characteristic of the channel that shows the process can also handle line of sight situation, and you will see these 4 tabs for this scenario as well. Now, let's show and compare this algorithm, the goodness of this algorithm of the approximation process. So we benchmark our machine learning clustering based algorithm with the baseline method against the original ray tracer channel. The baseline method is the K strongest path, which is basically the K strongest paths of the channel impulse response can be taken as to represent the channel. So as a performance criteria, we consider path loss and RMS delay spread that can quantify the larger scale channel characteristic. So you will see in terms of path loss, our machine learning base can deliver the same path loss as the ray tracer original channel. However, the strongest or baseline tab has around 3 dB approximation error with the original channel. In terms of delay spread, as you will see, our machine learning based algorithm can capture some good reasonable characteristic of the channel. However, the baseline method cannot do that. So as a conclusion, we developed a framework to create RF scenarios for real-time time domain FIR filter-based channel emulators. Our framework generates wireless scenarios from rich RF information derived from a professional grade ray tracer and optimally scale down the ray tracer output to a fewer parameters of the emulators. We evaluated and tested it on Colosseum for line of sight and non-line of sight scenario built with Remcom wireless inside ray tracer. Then we proposed framework. The proposed framework is able to capture the channel characteristics such as path loss and delay spread to a significantly more accurate level as compared to baseline models. Now, with this slide, let me open the floor for the question. You can find my email and this slide, and I will be more than happy to answer your question. Thank you so much. Hope you enjoy this presentation. Let me know if you have any question.